In this lesson, we look further at two-slit interference and we derive the path difference equations. As a reminder, in a previous lesson, we looked at how if we send plane waves at a barrier with two openings in it, then these two openings become coherent sources. Coherent sources meaning they have the same frequency for the associated waves, and also the waves have a constant phase relationship with each other. When we have two coherent sources like this, we can set up an interference pattern, and we see that here with the nodal lines and these antinodal regions. And if we were to look at the amplitude of the waves over here, we would see maximal amplitude here and zero amplitude here. Also, because light has wave properties, we've seen that we can do the same kind of thing with light. If we have monochromatic light incident on a barrier with two slits in it, then here you can see the same kind of thing with these nodal lines and antinodal regions. Also, if we project that light onto a screen, we see an alternating pattern of light fringes and dark fringes. We've also seen that we can change the spacing of those fringes by moving the screen relative to the barrier or vice versa, or by changing the separation of those two slits, or alternately by changing the wavelength of that wave, and here we do that by changing the frequency. So any of those things, changing the wavelength, the distance between the screen and the barrier here, or the spacing of the two slits, will change the spacing of the bright and the dark fringes. And that's all captured in one equation. And here's that equation here. S stands for the separation of the bright fringes. So if at the left we have our barrier with the two slits in it, monochromatic light incident on it from the left, and here's our screen, we're going to get an alternating pattern of bright fringes that are equally spaced with dark fringes in between them. And so S stands for the separation of these two fringes. D, little d, is the distance between the centers of the two slits, and big D is the distance from the barrier with the slits in it to the screen. And of course, lambda is the wavelength of the light that is incident on it. So now we're going to derive this equation to understand where it comes from, and also because there's some useful stuff that comes up along the way. So let me give you a bit of an overview of the logic of the derivation we're going to be doing, and then we'll go into more detail. Let's think about how this bright fringe gets here. It gets here by constructive interference of the light traveling from the top slit to this point and the bottom slit to this point. Again, constructive interference occurs when we have a crest overlapping with a crest. So let's think about the lines that the light is traveling along. The light from the top slit travels to the screen along that line, and from the bottom slit it travels along this longer line. Now, at the start, this point here and this point here have the light cresting at the same time. It's in phase, and so we need to somehow end up back in phase, back both cresting over here again. That's only going to happen if the light traveling along this longer path actually completes an integer number of wavelengths, more than the top one, in order to line back up. If it's anything other than an integer number of wavelengths, it's going to be in some intermediate part of the wave and not line up. Okay, let's unpack that in more detail. So here's a simulation to illustrate that. This is from O Physics. We have the barrier on the left with the two slits and the screen here on the right. And what we're seeing is light rays coming through the top and the bottom slit illustrated in green and in red, and every crest is given a dot so that we can follow the crests. And notice that if we look at this point on the screen, we see the crests line up exactly. The dots are overlapping. This is a point of constructive interference and would be a bright fringe. Also notice here that the wavelength of the light is given as 4 units. So every wavelength here to go from one crest to the next crest is 4 units long. Also notice that down here, the path difference, which is this distance here, is also 4 units. The path difference is the amount by which the bottom ray has to travel farther than the top ray to get to this point. If you think about this part here and this part here starting from the dotted line, those are the same length, but the bottom one had to travel this extra distance. That's the path difference. Here it's 4, it's exactly 1 wavelength, and that's why when they start off in phase, they end up in phase. This one's gone 1 complete wavelength longer and ends up back at a crest when the top one's at a crest. Now I can start that going, and I can move to a point higher up on the screen, and when I get to a path difference of 8 units, then they should line up again exactly. I haven't quite done it, but close, and you can see that here on the screen the two crests are lining up. This would also be constructive interference. This would be another bright fringe. But in between those, say in there, you see they're not lining up, and so this would not be the location of a bright fringe. So the path difference is the amount by which the bottom light has to travel further than the top, if we're looking up here, and when it's an integer number of wavelengths, we saw 1 wavelength and we saw 2 wavelengths, it's going to line up again, and we're going to get constructive interference and a bright fringe. So that's effectively an animation of this drawing here. Now what we're going to do is zoom in very close up to the two slits on this barrier, and so the screen is going to be way off to the right. Now although the two light rays here are angled and they're coming to meet at the point where the bright fringe is, if we zoom up very close here, they're going to look effectively parallel because the screen is so far off to the right. So that's what I've got down here. Here we are zoomed very close up to the barrier, and so those two light rays which above were angled are now effectively parallel, and we're going to treat them as parallel. I'm going to draw in here the midline, or line from the middle of in between the two slits out to the screen, which is way off to the right. And I'm going to draw another line here from that same point to the bright fringe. Now, these three lines, the line in blue I've just drawn and the two light rays, are going to eventually meet off at the screen, but when we're very close up, we can treat them as parallel. The angle here is the angle theta. And continuing my geometric construction, I can make a right angle triangle from the center of this top slit down to this light ray, where that's a 90-degree angle. And because this has got to be tipped by the same amount that this has been tipped, this angle in here is also theta. So there's a bit of geometric construction going on here. Now why am I doing that? Well, because this distance here, if you think back to the animation, is our path difference. It's the amount by which the light from the bottom slit has to travel further than that from the top slit to get to the point on the screen that's way over here where we're making a bright fringe. I'm just going to temporarily call that path difference x. This distance above we defined as d, little d. It's the distance between the center of the two slits. And now if you look at this triangle in here, I'm just going to shade it in so you can see it. If you look at that triangle there, then the sine of the angle theta is equal to the opposite over the hypotenuse. In other words, the path difference is equal to d sine theta. So again, the path difference, this right here, is equal to d sine theta, where theta is that angle between the center line and the line that connects to the bright fringe. We've already said that for constructive interference, we want that path difference to be an integer multiple of the wavelengths. Mathematically, we write an integer multiple of the wavelengths like that, n times lambda, the wavelength, where this is some integer, 0, 1, 2, etc. And we've now said we want that to be the path difference, so we just set that equal. And this is the first equation that we've derived. It's the equation that tells us where the bright fringes will be. That is, the bright fringes will all be at angles theta. There's the angle theta of each of the different bright fringes that satisfy this equation. So d is the separation between the two slits, and lambda is the wavelength of the light, and n we just plug in 0, 1, 2, etc., and then we can solve for sine theta and therefore theta, which is this angle. So if we have 0 over here, a path difference of 0, that's the middle bright fringe on the screen. If we put in a 1, we get the first bright fringe over. I'm drawing them here even though the screen would be way off to the right. And then etc., etc. That's for constructive interference in the bright fringes. For destructive interference, we have a different equation, and that's this one. And the reasoning is the same. We want to exactly not line up. We want crests lining up with troughs here, so we need a multiple of half wavelengths that's not an integer multiple. So again, this is 0, 1, 2, etc. And that's for destructive interference. Now these equations can be simplified, and we'll see in a moment, for two slits, and they'll give us the equation that we started off with above. But they're also good for using with multiple slits, like diffraction gratings, which we'll encounter in future lessons. And so they're more general equations. So that's something that's really helpful about these, besides just understanding where this comes from. But now let's actually use these to derive the equation above and see where that comes from. So once again, we're going to zoom back out. And when we zoom back out, I'm going to just redraw what we had above. We have the two rays of light meeting here, giving us a bright fringe at this spot. Now, in this drawing, the midline that I drew above looks like this, and the line to the center of the bright fringe looks like that. These lines are no longer parallel because we've zoomed way back out, but this is still the angle theta. Now, this distance is the distance capital D as we defined it above. And this distance we're going to call S sub n. It's the separation of this bright fringe from the midline. It's not the separation between adjacent bright fringes. There might be other bright fringes in here, for example, but it's the separation of this bright fringe from the midline. Now, if we think about this triangle, let me color in the triangle here for you. If we think about that triangle, we have the relationship that the tangent of the angle theta is equal to S sub n over big D, because this is a right angle triangle with the right angle right there. Now this is tan theta, and I have sine theta above, but it turns out for small angles, like less than 15 degrees approximately, tan theta is approximately equal to sine theta, and that's approximately equal to theta. Let me show you an example on a graph. So to illustrate what we call the small angle approximation, I'm using Desmos here to graph y is equal to theta, y is equal to sine theta, and y is equal to tan theta. And here is the origin. And so if you look close to the origin where the angles are small, meaning in here, the three graphs look identical. If I zoom in on that, you can see that this part here, the sine graph in blue, the tan graph in green, and just the theta graph, which is in red, are all effectively the same. And so for small angles, these three things are the same. Knowing that, as long as I keep this angle small, so I'm not traveling too far out here, I can replace tan theta with sine theta. So now I have sine theta is equal to S sub n over big D. Again, I can only do that if that angle theta is small. Now, here I have sine theta, and up here I have d sine theta. So I'm going to multiply through by little d, and now I have this. Now, if I go back above, the condition for constructive interference was that d sine theta is equal to n lambda. So this is equal to n lambda if I have constructive interference. So I'm going to make that replacement. This is equal to n lambda if I'm looking at bright fringes. So now I have n times lambda is equal to little d times S sub n over big D. And rearranging for S sub n, I get S sub n is equal to n times lambda times big D over little d. Now remember that this is the separation of the nth fringe. So this is the 0th fringe at the middle, the first, the second, the third. So in the drawing here, I've got the third one. I'd plug a 3 in there, plug in the wavelength in these two distances, and the equation gives me the separation of that third fringe from the center line. If I wanted to find the second one, so this distance here, the distance from the center line to the second fringe, then I would plug a 2 in there. And working algebraically, you can see then that the separation in between any two adjacent fringes, so this separation in here, which we called S, is going to drop that n entirely. So the separation between any two adjacent bright fringes is equal to lambda times big D over little d, and that's the equation that we got above. So that's the derivation for how we got it. It makes use of this small angle approximation, which we can only use in the case of two slits because the angles out to where the bright fringes are not very big. But when we get to more slits, we're going to end up with bigger angles, and we'll have to go back to these equations, which don't use the small angle approximation and so are more general. But now you know where the equations of two-source interference come from.